Hello everyone, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. In the lecture today, I am going to cover the basics of the LS and JJ coupling. In the LS coupling scheme, it is presumed that the orbital angular momenta of individual electrons add to form a resultant orbital angular momentum L, that is capital L. The individual spin angular momenta couple together in the similar way to produce a resultant spin angular momentum S. Then L and S combine to form the total angular momentum J. And as you can see from the figure, that this spin angular momentum total and this total orbital angular momentum, they are combining to give the resultant J along the z-axis. LS coupling predicts results in good agreement with the observed spectral details for many lighter atoms. The scheme of coupling may be visualized in terms of a vector model of angular momentum, that is J is equal to L plus S in the vector sum. So in sequence, let us first of all understand what is orbit-orbit interaction and how does this gives a capital L result. Consider orbital motion of two electrons, L1 and L2. Let us consider that they are their quantum numbers, and L1 star h by 2 pi, L2 star h by 2 pi are their angular momenta. L1 star and L2 star are quantized with respect to each other in such a way that they form a resultant L star, and L star is given by L star is equal to square root L into L plus 1. Now here, capital L will take values from 0, 1, 2, 3, 4, 5, etc. and the corresponding spectral terms will be S, P, D, F, G, H, etc. Now, let us consider an electron in the P, that is L is equal to 1 orbit, and other one in the D, that is L is equal to 2 orbit. Then all the integral values of resultant L from L2 minus L1 to L2 plus L1 are allowed. Accordingly, you can see from here, 2 minus 1 to 2 plus 1 will be 1, 2, 3. So L is equal to capital L is equal to 1, 2, 3, or spectral terms P, D, F will be there. Here, capital L star, according to the formula, L star is equal to square root L into L plus 1 will be root 2 for L is equal to 1, root 6 for L is equal to 2, and root 12 for L is equal to 3. Thus, what we see, the two vectors L1 star is equal to root 2 and L2 star is equal to root 6. They combine in such a way that the resultant can orient in three positions, that is L star is equal to root 2, root 6, and root 12. Just we have considered the orbit-orbit interaction. Let us consider now the spin-or interaction first. With two electrons, each having a spin angular momentum S star h by 2 pi, where S star is equal to square root of S into S plus 1, and S is equal to half here, and that is for both the electrons. There are two ways in which a spin resultant S star h by 2 may be formed. S1 and S2 are spin quantum numbers of two electrons. This implies S1 star is equal to a square root half into half plus 1, that is half into square root of 3. And similarly, because S2 is also half, S2 star will also be half into square root of 3. The two resultant quantum numbers are S1 minus S2 and S1 plus S2, that is capital S is equal to 0 and capital S is equal to 1. Here it may be noted that S is equal to 0 gives rise to singlet, and S is equal to 1 to triplet. Now, let us consider a table, and that will summarize the whole situation about two electron system 1s2p. Now, what are there in the table? Let us discuss that first. To derive the term symbols for the different spin orbit states, we first need to calculate the total orbital angular momentum and total spin angular momentum from those of the individual electrons respectively. Then L and S, capital L and capital S, are combined to find the total angular momentum of this group of electrons, that is capital J. The possible combinations of L, S and J will be given as following, that will be applying in the table. Capital L is from L1 minus L2 to L1 plus L2 in integer steps. Capital S is S1 minus S2 to S1 plus S2 in integer steps. And capital J is L minus L, S to L plus S, again in integer steps. Now this is table for LS coupling of 1s2p electron. As we can see over here, that this S stands for L1 is equal to 0, this, and P stands for L2 is equal to 1. Spin S1 is equal to half and spin S2 is equal to also half. Then we have the value of resultant capital L will be either it is L1 minus L2 or L1 plus L2, both will be 1. So capital L is 1, whereas capital S, that is half minus half is 0, and capital S, half plus half is 1. So we have one value of total angular momentum, the total orbital angular momentum capital L, that is 1, and we have two values of a spin orbital or spin momentum, and that is S is equal to 0 and S is equal to 1. Now naturally, for S is equal to 0, the terms will be singlet, and for S is equal to 1, the terms will be triplet. Now let us see. Let us consider the combination L and this S. So we have L is equal to 1, S is equal to 0. So L minus S and L plus S both will give J value as 1. So we have S is equal to 0, so it is a singlet term. We have L is equal to 1, so it is a P term, and J is equal to 1, that is here. The multiplicity is written as the superscript on the left hand side, and the J value is written as the subscript on the right hand side. So the result of combination of capital L is equal to 1 and S is equal to 0 will be a singlet P1. Similarly, let us consider another combination L is equal to 1 and S is equal to 1. So this L minus S to L plus S will give the value of J as 0, 1, 2. Now because we have S is equal to 1, so all the terms here will be triplet. And we have J values as 0, 1, 2, and we have L is equal to 1, so it will be a P level. So we have for all these three values, and S is equal to 1 as triplet, triplet P0, triplet P1, and triplet P2. So thus we have these terms, that is one singlet and three triplet coming out of the combination of 1s2p electrons through the LS coupling. Now the explanation once more. The term symbols are composed by writing the total orbital angular momentum L in a spectroscopic notation, that is S, P, D, F, etc. They are all capitalized for two electron or other system. Since this refers, of course, to the total orbital angular momentum. Now, the total angular momentum J is written as a subscript. The spin multiplicity 2s plus 1, as I have written, is calculated from the total spin and is attached to the term symbol as a leading superscript. The term symbols for all four terms in 1s2p configuration that we have seen in table 1, and in here we have one singlet, one P1, and three triplets, that is 3P3, 3P1, 3P2. Now, in principle, any other electron configuration can be treated in exactly the same way as we have seen in the last table. Although, of course, the number of different terms can become quite large. We have again a table 2 for the combination 2p, 3p. Now let us go straight to the table. Here we have 2p, 3p. So L1 is equal to 1 for 2p and L2 is equal to 1 for 3p. S1 is again half and half, S2 is half. So capital S is 0 and 1, but capital L, that is L2 minus L1 to L2 plus 1 is 0, 1, 2. So we have two values of capital S. S is equal to 0 giving all terms that are singlet and S is equal to 1 giving all terms that are triplet. And we have L values that is 0, 1, 2. So L is equal to 0 will give S term, L is equal to 1 will give P term, and L is equal to 2 will give D term. So here we have made the combination like this. S is in the column 0 and 1 and L is in the row that is 0, 1 and 2 from here. Now L is equal to 0 means capital S term, L is equal to 1 capital P and L is equal to 2 capital D. Now we have to make a combination. Let us say first combination is capital S is equal to 0 and L is equal to 0. Naturally, we will have J value 0. And because S is equal to 0, it's a singlet term and this is S and J value is 0. So this is singlet S 0. Now if we make a combination with S and J P, that is L is equal to 1. So we have J value as 1 only. So we have again, because it is S is equal to 0, it is singlet, it is P and J is equal to 1. Similarly, if we make a combination for S is equal to 0 and L is equal to 2, that is D, then naturally this is again be a singlet term, D is a spectral term, and because J is equal to 2, so singlet D2. Now let us go for S is equal to 1 and different values of S in the row, different values of L in the row. So S is equal to 1 means all the terms now will be triplet. And L is equal to 0 and S is equal to 1 is going to give J is equal to 1. So now we have triplet because S is equal to 1, S 1 because J value is 1. But if a combination is made between L is equal to 1 and S is equal to 1, then J values will be 0, 1, 2. Because S is equal to 1, it is triplet. P terms are there. So triplet P 0, triplet P 1 and triplet P 2. Much in the same way, if capital S is equal to 1 and capital L is equal to 2, that is D term, then the J values will be, we have 1, 2, 3 and all these will be triplet. So we have J values will be 1, 2, 3, triplet D1, triplet D2, triplet D3. So we have, because due to a combination of 2p, 3p electrons, we have 3 singlet and we have 7 triplet. Now let us go for JJ coupling. For heavier atoms, we have another coupling scheme called JJ coupling. And this provides better agreement with experimental results in spectroscopy. In JJ coupling, the orbital angular momentum L and spin angular momentum S of each electron are first coupled to form a total angular momentum J for that electron. These single electron total angular momenta are then combined into a total angular momentum capital J for the group of electrons. For example, J1 is equal to L1 plus S1, J2 is equal to L2 plus S2, and capital J is equal to summation of all the J's. Thus, in contrast, this is in contrast to the LS coupling, where the total orbital angular momentum capital L and total spin angular momentum capital S of the system are calculated first and then combined to give the total angular momentum J. In general, the results from both coupling schemes are different. For example, for the 1s2p configuration, JJ coupling results in 2 doublet rather than a singlet and 3 triplet. For 1s electron, J1 is equal to L1 minus L1, S1 and L1 plus S2 both will give J1 is equal to half. And for 2p electron, we have J2 is equal to, you see, L is equal to 1, S is equal to half. So J2 will be 1 minus half and 1 plus half, that is half and 3 by 2. So we have J1 is equal to half and J2 is equal to 3 by 2 and half both. So let us consider the combination as in table. J1 values are given in the, J1 is given in the row and J2 in the column. So let us make the combination. J1 half and J2 half together will combine to give half minus half is equal to 0 and half plus half is equal to 1. So J values are 0 and 1. Similarly, half and 3 by 2 will make combination to give 3 by 2 minus half is equal to 1, 3 by 2 plus half is equal to 2. So we have the combinations like half here, half here, J is equal to 0, so subscript. Then we have half 3 by 2. Then we have one combination we can make half and half J is equal to 0, half and half J is equal to 1, half and 3 by 2 J is equal to 1, half and 3 by 2 J is equal to 2. So we have these spectral terms coming up over here. Now, in the same way, let us consider PD electrons. We have for PD, P electrons, S1 is equal to half, L1 is equal to 1. So J1 is equal to half or 3 by 2. Similarly, for second electron, D electron, S2 is equal to half, L2 is equal to 2. So we have J2 is equal to 3 by 2 and 5 by 2. Then combining these four values in all possible ways, that is J1 is equal to half and 3 by 2, J2 is equal to 3 by 2 and 5 by 2. What do we get? Now, J1 is equal to half and 3 by 2. J1 is equal to half and 5 by 2. J1 is equal to 3 by 2 and J2 is equal to 3 by 2. J1 is equal to 3 by 2 and 5 by 2. So these four combinations are given. Now this combination, J1 is equal to half, J2 is equal to 3 by 2, gives J value as 1 and 2. J1 is equal to half and 5 by 2 will give J is equal to 2 by 3. J1 is equal to 3 by 2, J2 is equal to 3 by 2 will give J is equal to 0, 1, 2, 3. And 3 by 2, J1 is equal to 3 by 2, J2 is equal to 5 by 2 will give J values as 1, 2, 3, 4. Energy states in terms of JJ coupling, how can we write down? For PD electrons, then we have, these are the combinations we have. That is, J1 is equal to half, J2 is equal to 3 by 2, J value is 1 over here. J1 is equal to half, J2 is equal to 3 by 2, J value 2. Similarly, we have J1 is equal to 3 by 2, J2 is equal to 3 by 2, J is equal to 0, 3 by 2, 3 by 2, J is equal to 1, 3 by 2, 3 by 2, J is equal to 2, 3 by 2, 3 by 2, J is equal to 3. And similarly, for these ones, half, 5 by 2, 2 and 3 we can make. For this 3 by 2, 5 by 2 we can make J is equal to 1, 2, 3, 4. And all these capital J values will be written as superscript outside the bracket. These J values, J1, J2 values are written in bracket and capital J values are written as subscript outside the bracket for all these terms. So this is how we have explained about the LS and JJ coupling. Thank you very much for your kind attention.